Lecture 13, Dependencies and Speculation. We're going to talk about dependencies in this context, and we don't mean necessarily software dependencies as in you require this library in order to compile your code. What I'm talking about is more along the ideas of there are some things that have to take place in a certain order, and dependencies are limitations to parallelization, so if a computation has to be done as first step X and then step Y, we have to do it correctly, otherwise we get the wrong answer, and we don't want the wrong answer. I mean, getting the wrong answer is not acceptable, and that's the kind of thing that we don't want. But there is a correct order between doing these steps, and doing it wrong gives us the wrong outcome. If you don't believe me, if you want to bake a cake, you have to mix all the ingredients and then bake it. You don't bake all the ingredients and then mix them. Whatever you get then isn't a cake. And I suppose it would be entertaining in some sense to show the result of mixing the ingredients after baking them, but it kind of would be a waste of some ingredients. So maybe I won't do that, even though it might make for a funny insert into this video. We're going to assume for now there are no synchronization problems that are sort of getting in the way of what we want to talk about, so there's no deadlocks or anything like that, but we're interested in identifying what things that we could run in parallel. And to give you some analogies for some things that would appear in real life where there are dependencies, if you want to take your bike somewhere, you have to extract your bicycle from the garage before you close the garage door. It's not super practical to try to put the bicycle through the garage door. I mean, once, maybe. Must close washing machine door before starting the cycle. If you're doing laundry, the laundry machine just won't start if the door is open, assuming, of course, it is a reasonably modern one. I suppose really old ones probably had no such problem, and you could start it anyway, and free floor washing, I suppose. Maybe not ideal. However, that's not what you want. Must be called on before answering questions. In a lecture hall anyway. If you put your hand up to suggest an answer, maybe. But of course, people can shout out an answer, and that isn't necessarily a sort of strict dependency. And last one, students have to submit an assignment before, say, the TAs can mark that assignment. That's also in the sort of category. I can assign you a grade of 0 if you didn't submit an assignment, but I assume you don't want that. I imagine you consider that to be the wrong answer, because we did things in the wrong order. Mark first, submit later, doesn't do what we need it to do. Okay. And the other kind of dependency, and I said this is not the kind that we're talking about that you are familiar with, is the package dependencies that are very common in software these days. In Rust, we manage them with cargo. In Python, with pip. In Node, Node downloads half the internet, including all kinds of hilarious packages, including is even, and occasionally package manager dependencies, as depicted in this XKCD comic, cause strange things to happen, especially in ecosystems like the JavaScript world, where there are 8 billion packages, and sometimes a tiny insignificant package becomes relied upon by lots and lots of other packages, directly or indirectly, and somebody who has control over that seemingly insignificant package does something nasty with it, and then you have a problem because, oh no, it's now stealing credit card information or something. That's not the kind of dependency that we want to talk about, even though we're going to talk about breaking dependencies a little bit later on, and you should definitely break your dependency on any such package, but that's not where we're going with this. We're talking about inside of our program. And there's two kinds of dependency that we want to talk about, and they are loop-carried and memory-carried dependencies. And the first we'll start with is a loop-carried dependency, and what we're talking about here is when an iteration of the loop depends on the result of a previous iteration. So if in our vector here, all values in our 32 capacity vector are initially 1, then can we do these in parallel? Now, vector at array index 4 is vector at array index 0 plus 1. Vector at array index 5 is array at 0 plus 2. Yeah, that totally works. There are no dependencies between these two lines. There's nothing that happens on the first line where vector at index 4 is being assigned that has any impact on what happens at vector at array 5. This is not typically how we use arrays. There are usually more things we do with arrays than this, and so it is perhaps not perfectly representative. But what about this? If we now iterate over it and we say for I in 1 to vector.length, vector at array index I is the previous position in the vector plus 1. Okay, that's obvious. If our array here, it's A in the slide, but should be vec. At index 2 is 3, and if we get it wrong, if we swap the order of a couple of statements, we get the wrong answer, because each statement, if you wrote down the loop steps individually, so instead of writing it as a loop, but you did it just the unrolling of that loop, where you said, okay, vector at 0, and vector at 1, and vector at 2, and so on, it would show you that each step is dependent on the previous step, because we need the value that is assigned there to actually do the next assignment. And that's an example of a loop-carried dependency. That's maybe a silly example. What about a real example? Well, here is a Mandelbrot calculation, and we are computing whether a complex number x0 plus I, or in engineering notation j, y0 belongs to the Mandelbrot set. So, given this code, we take an initial x and y, both as 64-bit integers, and we calculate. Repeatedly square the input, return the number of iterations before the absolute value exceeds 4, or 1,000 iterations, whichever is smaller. So we set our iterations count as 0, and we will take a copy of our initial values x0 and y0, because we're going to change them. And then we'll calculate x squared as x times x, and y squared as y times y. And while x squared plus y squared is less than 4, and iterations is less than 1,000, we will do a little calculation here on it and increase the number of iterations. How do we parallelize this? The answer is you don't. Not really. Each individual point, there's a lot of dependencies here. All the changes to x squared and y squared and everything produce a lot of dependencies on iterations of the loop, so that you can't just split this up somehow. What we can do, however, is parallelize at a point level. So we can call the function with lots of different initial conditions as the different values, and that will be possible to run in parallel, because the result for any pair of initial conditions is independent of the result for any other pair of initial conditions. So this function, being, as we've recently discussed, pure, is exactly the kind of thing where you could parallelize this function and you could iterate over 1 million points and do those all in parallel without any issue. Sounds good. For any particular combination of x0 and y0, that one has to be sequential, which maybe is unfortunate. Consider now a slightly different example. Is this parallelizable? For I in 4 to vector length, can we do something like this, where the vector at index I is that of I minus 4 plus 1? The answer is sort of. that we could do this for up to 4 statements in parallel at a time, because of the fact that we're always looking significantly behind in the array. So vector at index 4 is calculated as vector at index 0 plus 1, vector at index 5 is vector at index 1 plus 1, and so on. And we only run into a slight problem when we need the value that we've computed in vector at index 4. So we could say here that array accesses have stride 4. There are no dependencies between adjacent array elements, but there are dependencies between array elements that are separated a little bit more, which allows a limited amount of parallelization in this case, in which we could potentially do up to 4 of these calculations in parallel. All right, we'll take it. The other kind of dependency that I wanted to talk about is the memory carried dependency. And the memory carried dependency is, it's similar to the idea of loop carry dependency that we've already talked about, but instead of it being between iterations of the loop, it's about the order in which 2 memory accesses occur. So if we've defined a count as a structure that has a balance, and your balance is 0, initially, and then we have functions f and g, and f adds $50 to your balance, and g increases your balance by 1%. So the first one is somebody deposits some money in your account, and the second function is monthly interest calculation. Not that banks really pay you any interest on your checking account at this stage, but pretend that this could even be a savings account. It just says account. And they are super generous to you with their amazing 1% interest. Let's imagine. So there are a couple possible outcomes after executing G and F if they run in parallel threads. Obviously, we would have to assume that things are wrapped in atomic reference counted type, so we could pass the account structure to different threads, and we would have a mutex around it and all of that. But if we did that, what are the possible outcomes? Well, one possible outcome is that the account is $50 because, well, what we see is that we have done the G function first, in which case 0 times 1.01 is still 0, and then we add 50 to it, so our total is 50. The other possible outcome is that we end up with $50.50 because, well, we go through and the f function runs first, so the balance is set to 50, and then we do the 1.01 multiplication, which adds 50 cents, and we therefore have a total balance of $50.50. A difference of 50 cents, of course, is not huge, but if you had a significant account balance, that could be a meaningful amount of money. So, the order in which these things happen could be interesting. Now, if you're cynical about banks, you will assume that they will do the interest calculation first, because then they get to keep the money that they would otherwise be depositing in your account for interest. Maybe, maybe not. Okay, so to think about memory carried dependencies, you should think back to our earlier discussion about hazards, because, well, memory carried dependencies are hazards. There's no read after read dependency, so that's not anything really to worry about. But when we have a read after write, or a write after read, or a write after write dependency, all of those things are memory carried dependencies, because we're talking about, are we writing to or reading from a memory location in the correct order. So anything that we know about identifying that kind of dependency is, or that kind of hazard, is going to be useful in identifying, does there exist a memory carried dependency here or there. So if you want to take this idea and apply it to your program, we'll introduce, just for context, the idea of a critical path. And probably you are familiar with critical paths from other courses, depending on which capstone design project and which department you're in. You may have had to create one of these for your project. And it is saying there are a whole bunch of tasks that are necessary between the start and the finish. And given a sufficiently described plan, you can make a nice chart or a nice graph out of it, where it says, okay, at the beginning we have tasks A, B, C, and D to do, and tasks S2 depends on B and C, and S1 depends on A, and to get it all done we have to finish D, all those things. And B depends on A, C has no dependencies, D depends on both B and C in this diagram, and we could in principle execute A and then B in parallel with C, and by identifying what these things are in our program, we can identify what is the critical path, what is the slowest step, what is limiting our ability to speed things up. Having this diagram, it makes it easy to see what can run in parallel and also what things have to happen in what order. For our fourth year design project, this would be many years ago, we had a very complicated Gantt chart to the point where we tried to print it and it crashed to printer. So that was not good. We thought kind of hard about, like, all right, how do we get around this problem? And then we figured out we could just take a screenshot of the Gantt chart and print the screenshot, because the PNG image of it, that was easy for the printer. But the actual Gantt chart, was like a vector graphic with all the lines and bars and everything, was just way too much. And we made a university printer very sad, for which we are still sorry. Things happen. You might not need such a diagram, and in particular, if you're looking at a piece of code, you're probably not going to break out some sketching software or pen and paper and draw yourself a very complicated diagram of here are the dependencies A, B, C, and D. However, they are very useful for explaining to non-technical coworkers and or senior management what's happening and how it's going. So you may be well advised to do that just for the sake of keeping everybody up to date on how your project is going and visualizing what's happening. In any case, by knowing what is your critical path, by knowing what things are able to run in parallel and which things are the slow steps, it could give you some insight into, well, how to speed up your program using the technique we're going to talk about, which is speculation, breaking dependencies by speculating. Okay, so speculation. We already introduced the idea just a little bit when we talked about what happens with branch prediction, because hardware architecture does this. We don't know whether a branch is going to get taken or not, but we're going to take a guess, roll the dice, and see how we do. There are, of course, techniques that we use to make sure that our guess is good, that we're not just randomly guessing. And as we saw in the discussion of hardware, we actually get pretty good at it, and we get reasonable results for our efforts. So, roll the dice and see how we do is maybe a bit negative of a perspective on this. So here's a coffee analogy. A real-life analogy on speculation. So if under normal circumstances the coffee shop staff waits for you to get to the front of the line and place your order, suppose you want a medium double, they wait for that and then they start making your order. That is sensible. If you go to a certain coffee shop enough, then the staff get to know you, and they might know your typical order, and they could potentially speculate what your order will be and start preparing it in advance even before you get up to the counter. If they're right, time is saved because your order is ready sooner, and if they're wrong, then the staff did some unnecessary work and they'll throw away the result and start again with what you did order. And if they can predict with high accuracy what you're going to order, that's a net savings of time on average. You can even put some numbers on this. If successfully predicting your order saves 30 seconds per day, and if they're wrong, remaking it takes 3 minutes longer than normal, and suppose your order is unpredictable 1 out of every 10 days, how much time is saved? Well, 9 days are correct, so your savings is 4.5 minutes, from which we subtract the 3-minute penalty for being wrong, and we save 1.5 minutes in a 10-day period, and that's about 15 seconds per day on average. That's not huge, but imagine if the coffee shop can do that for every regular customer. If there are, say, 100 regular customers who come in every day, that's 25 minutes of waiting saved per day. It all adds up. I suspect even that my estimate of 100 regular come-in everyday customers is kind of low, given that coffee shops are generally pretty busy places and people are very eager to have their caffeine in the morning. So you can imagine that even a small improvement in this area can have a very significant impact because ultimately, if it's a busy place and you're waiting in line, any time saved for the person ahead of you is also time saved for you. And we don't even take that into account in this calculation of 25 minutes waiting saved per day because, well, we'd have to have some model for how many people are waiting in line. Let's say for the moment that we don't, although we will revisit that kind of thinking a little bit later on. Okay, let's not get too distracted in our coffee analogy. Let's think about how do we speculate. So we know that we don't need to wait for a branch to be evaluated, and we hopefully took away from a discussion about hardware some of the key ideas that are important here, which are basically that we are going to guess about what will happen, and if we're right, we keep the result, and it is a win. If we're wrong, we have to go back and do what actually was correct instead, with a slight penalty. And we're going to use speculation to, well, parallelize code. And by that, I mean there are two specific approaches. We'll call them speculative execution, and the other is value speculation. So speculative execution we'll start with first, and we'll consider the following code. So if val is equal to long calculation of x and y, and if this value is above a threshold, then we return val plus second long calculation of x and y. And we need to run this under the circumstances of, well, if value exceeds this threshold. Without too much more information, we don't really know whether or not we're going to have to execute second long calculation or not. It really depends on the return value of the first function, so we're not sure. And normally we would have to wait. We'll figure it out eventually. But of course our goal is to speculate. And can we do that here? Well, yes, actually, we could. We'd have to have a couple of assurances about things, and one of them is that the input to second long calculation doesn't depend on the output of long calculation, that they both take x and y as parameters, and they're unchanged, so alright, we're good in that regard. That's one thing. Another thing that's interesting to think about, though, is, well, how do we do it? So what we'll do instead is spawn a thread that returns long calculation x and y, and we'll then create a second thread that does second long calculation also of x and y, and then we will join both threads. If value exceeds the threshold, then we return val plus v2, otherwise we return val. So we did both calculations in parallel and returned the same result as before, so our answer remains consistent. But we did some work. Some of it in parallel, some of it was extra, some of it was unnecessary. You see, there are, of course, cases where we didn't need to calculate second long calculation at all, and we did it anyway. Is that a big problem? Well, that depends. I mean, if your system is at its capacity, using 100% CPU, and we're doing this extra work, that's not good, because we are wasting CPU time for something we don't need. But that's not usually the case. Usually you have sufficient CPU around that you could afford to spare a little bit, where we do some extra work in service of speeding up the results for people who are interested in the data. So yeah, we can usually do this. There are a couple of assumptions about long calculation and second long calculation. for this to work. And one of the things that is important about that is that, well, they don't interfere with one another in some way. That is, there's no side effect from, say, calling the first long calculation function that really changes how second long calculation would work. That is usually not a safe assumption, because we would have to actually look in the code of these two functions to be sure. But in Rust, because the side effect stuff and global state is somewhat discouraged, we can have a bit more certainty than we normally would in another language about this. However, it's still worth checking. So can we improve? Yeah. The current thread is also a valid thread in which to do work, and we don't actually have to create two threads and join two threads. We could actually reduce our amount of overhead by having the current thread run the first long calculation, and then the second long calculation be run in its own thread, so we only have to create and join one thread. Slight improvement, maybe less overhead. This is the kind of thing where I see sometimes in assignments, exam questions, where people create one thread for each task and join each of them, and you can think to yourself, like, is that the best possible way? For sufficiently long calculations, it doesn't matter very much, because the overhead of creating and joining the thread is small in comparison to the actual work being done. But it is important to remember that the thread that we're in is valid for doing work, and it's okay to not create a thread for it specifically and just use the one we're already in. But it's not wrong either. So, potential micro optimization that could appear here. Anyway, to put some numbers to our improvement is not too difficult. If we have T1 and T2 as the time to run long calculation and second long calculation, respectively, and P is the probability that second long calculation executes. In the normal case, we have it's T1 plus P times T2, which gives you the average time that it's going to take to execute. And the speculative code takes the maximum time of T1 plus T2 plus S, S being the synchronization overhead, that is the time to create and join the threads. Our hope, of course, is that S is small in comparison to T1 and T2, in which case then it's negligible and you could ignore it, but we put it in there for completeness so that you don't overlook that, because it is non-zero. And so you can basically do the math on when is speculative code faster or slower by putting some numbers to it and sort of working out what is the break-even point between these two things. And it depends, of course, on how likely it is we have to execute the T2 code and how long that's actually going to take. And could we improve it? Maybe. Okay. Now, speculative execution is interesting and is a good technique. Sometimes, as I say, we do a little extra work we don't need, but we can usually live with that because we're not so short on CPU that we have nothing to work with here. But here's a case where speculative execution won't help us. We have a true dependency between these two functions in that we have to do long calculation on x and y and it returns a value, and then we return second long calculations result, which takes val as its input. So what do we do now? Speculative execution won't help us here because we have to take the result from the first one. So any ideas? Okay, well, I told you about value speculation already, and that's kind of the idea that we are going to think about. If the value is predictable, that is to say, in most cases, we know what val is going to be, or if it is likely it's going to be the same as it was last time, then we could use that and we could speculate that, all right, if this hasn't changed, we'll do the same thing. If 90% of customers are using the standard billing plan, you can assume that that's what's going on in your calculations, and if it later turns out that's wrong, you just fix it. Or you have a software cache where you keep the latest state so you don't have to go to the database to check a value that changes rarely, something like that. So here's code that does value speculation. Given x and y and the last value, then we will create a thread that says, all right, do the second long calculation with the last value. We will then start the long calculation, join the other thread. If we were correct, and so the returned value of long calculation is the same as it was last time, we've got v2 in hand already, and we can use it. Otherwise, we call second long calculation with value, and we get the actual correct result. Okay. This is a little bit like memoization, remembering previous outcomes so that we can reuse them when necessary, but we added a little sprinkle of parallelization in there, and that we create a thread up at the beginning of this function. So, are we going to be correct? Well, as I say, if the last value is going to be valid for some period of time, then we might save some effort here. If, of course, it's going to be different every time, this isn't very helpful. And again, to estimate our impact of value speculation, if t1 and t2 are unchanged from last time, they are the times to run the functions, and p is now the probability that we have to execute second long calculation a second time, because we were wrong, and s is our synchronization overhead. In the normal case, these are sequential. It's t1 and then t2, and then the speculative code takes the maximum of those two, plus the synchronization overhead, plus, in the occasion that we are wrong, the cost of doing the second calculation over again. Once again, as a little thought exercise, you could put some numbers to this and figure out at what point, when is the speculative code faster, and when is it slower, and you will, again, be making certain assumptions about how often we have to do the second calculation again, and how long the second calculation takes. And the things that we've discussed about when we can speculate is, well, because it's not always a good decision to do this, we have to be sure that long calculation and second long calculation don't call each other, and they don't have some shared state that they are modifying, and also the return value of long calculation must be deterministic. That is, given the same inputs, we get the same outputs. So as the general warning, you have to think about the side effects of these function calls to make sure that nothing really weird happens that would change the outcome, so that the parallel code would be different from the sequential code. Side effects are problematic because they are unpredictable, and it can be unavoidable. Rust discourages that kind of thing, but it doesn't forbid it. You can still have atomic types that are shared that are some global state, so we do actually have to read the code of long calculation and second long calculation to be sure that they don't fall into any of these bad patterns. And on the subject of side effects, there's well, hopefully a lightly amusing comic about it, just repeat our warning about considering side effects of calls.